Okay, so welcome back to the benzene substituted lecture, and you've just experienced the nomenclature round of the lecture, and I think that you probably feel okay with this stuff. I know that you do. You don't have to tell me. I can just feel it. I feel it through the computer speakers and the microphones and your headphones that you're using. I know that you're going to be good with it. So in the next part of this lecture, the next half, is going to focus on reactions. We've already talked about reactions of benzenes, right? There were 5 of them. Do you remember those 5 reactions that we talked about when we were introduced to benzene back in the previous lecture module? Well, I hope so, because I told you they were coming, and you probably flipped back to your notes. I hope you did. And you saw that there were 5. And the 5 was halogenation, nitration, sulfonation, acylation, and alkylation. So these were the 5 that we talked about when we discussed benzene. Because remember, we said that benzene, just as benzene, was very, very snooty. Ew, the nose stuck up in the air. I don't want anything to do with anybody. I mean, that's what benzene basically does. It's very stable. It doesn't need to react. There's a lot of delocalization that's happening in that molecule. If you break a bond, because they're kind of like double bonds in there, not really, but kind of. And if you break one of those double bonds, it destroys the delocalization, so it doesn't want to happen. No addition reactions take place. A substitution reaction takes place instead. And all of these gave us a substitution reaction. Remember, this bond, or any of those bonds, has a hydrogen. And these reactions basically went in and said, hydrogen, you gotta go. Hit the curb. Boink. Off it goes. And then we replace that with something in its place. Of course, that something is an electrophile. So halogen, or a nitro group, or an SO3H group, or the acyl group, or the alkyl group, all went on to that spot. Substitution. That's what happened. Okay, so with that said, that was benzene. That's what benzene did. I'm not really working with benzene anymore. We have benzene with other things on it. So for instance, let's say there's an NO2 on here already. That is a substituted benzene. Now what happens? Same 5 reactions? Do they do the same thing? If so, where does the incoming group go? That's the biggest question in these. So if I halogenate that, number 1, can I halogenate it? Number 2, if a bromine goes on there, which one would it go to? I mean, there's 5 different choices, right? Or are there not 5 choices? Is there a limited number of choices that can accept the bromo group, or the nitro group, or the SO3H group, or the acyl group, or the alkyl group? Where are they going to end up? So these are the questions that we have to answer when we talk about the world of a substituted benzene. So just as a recap, this is what we have talked about in the benzene world at this point. Halogenation, added Br2 with the catalyst, and that added on a bromo group to our benzene. The nitration took benzene, nitric acid and sulfuric acid, in order to add on NO2. The sulfonation reaction took benzene, sulfuric acid, and heat. That added on an SO3H group. Our acylation and alkylation were very similar. The difference is that the acyl group involved the C double bond O, and the alkyl did not. It was just a random carbon chain. Each one of these used aluminum chloride in the catalyst, but the acylation also required water to prevent some buildup of some contamination efforts and byproducts that we needed to take care of. In each case, a carbon went on to the benzene ring, and in the alkylation part, just the carbon chain went on. In the acylation part, the C double bond O went on, and it carried with it the rest of that compound. So literally, the chlorine goes away in each one of these cases, and the remaining piece gets added on to the benzene. Folks, this is what we talked about. This is what we have discussed in the previous module. And in the words of Celine Dion, it's all coming back to me now. So if a benzene that's not just benzene, let's say there's already a bromo group on here. Or let's pretend like on this benzene structure there was a C triple bond N on here. Should have wrote that backward, but you get the drift, you get the picture. On this benzene ring, let's say there was an OH group on here. On this benzene ring, let's say that there was something else on here already. Let's say a C double bond O with an H. And this benzene ring, let's say there was an NO2. How does it change? What goes on? Does it change? Or am I leading you up to something that you're feeling nervous about, and then just to kind of make you happy in the very end to say nothing really does change, you keep doing what you're doing? Well, the answer is kinda. We kind of do the same thing. Bromine gets added on, the NO2 gets added on, the SO3H gets added on, the C double bond OR adds on, the R adds on. They all add on just like before, so that makes you happy. But they just can't go wherever they want to go. That's the issue. They can't go wherever they want to go. All right. So that means there's going to be extra to the story. There's got to be an extra set of rules that come along with benzene structures that already really have something on it in the first place. So before we really start understanding how the substituted benzenes react, I want to talk about benzene as a whole first. Just simple little old benzene. Not going to hurt anybody except give you cancer. So this benzene ring is loaded with an alternating double, single, double cause of trouble bonds. All right, well, they're loaded down with electrons because those electrons are coming from all of those extra bonds. And those electrons are negative, right? And when we have negative things like this in organic chemistry, we've always called these things nucleophiles. All right, so benzene is a nucleophile. And we now know why. We've also talked about this already because in the previous set of reactions with the magic 5 for benzene, those magic 5 basically required a positive piece. And that positive piece was an electrophile. That electrophile was required because opposites attract. It carries a positive charge. The positive charge comes into the ring and it's attracted to that ring because that ring is a nucleophile. So the nucleophile and the electrophile react together in a substitution reaction to remove a hydrogen and replace that hydrogen with an incoming group. Whoa, that was a doozy, wasn't it? Big boy talk, big girl talk. So the concept here is that if something else is attached to the ring, could it change the way that benzene reacts? And of course the answer is yes, it can. Because there's now something else other than just benzene. And the group is going to be very important. And the group is going to be broken down into two classifications. The first classification is called an activating group, and the second classification is called a deactivating group. Well, that's easy enough. What do you think an activating group does? It activates the benzene ring. What do you think the deactivating group does? It deactivates the benzene ring. That's not very difficult, folks. I hope you don't miss that on a test. Okay, well, we got to do a better job than that to define them. But I think you're forming a picture here of the direction that we're going in as far as those groups. If we have an activating group, then that means it increases the reactivity of benzene. Remember, I said that benzene was, ew, I don't want anything to do with anybody, right? That's what benzene does. But an activating group prevents it from having that attitude. It was raised the right way. It had some good parents. You don't treat others that way, benzene. Just because you think you're better than everybody else doesn't mean that you are better than everybody else. So it wants to play. It wants to interact. The activating group allows that to happen. The deactivating group, that's a different set of parents. They have raised their child, benzene, up in a different way. And if you think, ew, I don't want to play with anybody at any time is bad enough, then try taking it another level higher. They don't want anything to do with anybody because they think they are better than everybody else. So the deactivating groups, if they're present, will drastically decrease the reactivity of benzene. It makes it harder to react. So activating groups increases the rate of the reaction, and deactivating groups decrease the rate of the reaction. How do they do this? All right, well, I need to make a better nucleophile. If I have an activating group, what has happened is that benzene has become a better nucleophile. That kind of makes sense, right? I mean, if this group, whatever this group is, onto the benzene ring, this is a nucleophile. A nucleophile is the reason that it reacts with an electrophile. If this group makes this a better nucleophile, then it's more willing to react with the electrophile. So that means with a deactivator, that means that this benzene group becomes a poorer nucleophile. Okay. Well, how does it do that job? How does it make the benzene better or worse? All of that deals with are electrons. Because nucleophiles are negative. So if this group has some electrons that it can donate to the ring, well, that makes benzene very happy. The reason it makes benzene happy is because delocalization now can go up into that group and on back around. Not only does it make benzene happy, but there's more negative now that's associated there, which means that it's a better nucleophile because that's the definition of the nucleophile. So if the group has electrons, and those electrons can be donated to the ring, that is an activator. That's all that it is. If the group, though, sucks the electrons out of the ring. We've got some electrons in here and they come out. Then that is a deactivator. And the reason that it's a deactivator is because it is messing with the delocalization of the benzene that is present. It's messing it all up. Benzene doesn't know how to handle it. I mean, it's getting sucked of electrons, and it can't really fulfill the need of anything else except for that group. Because of that, those electrons are getting sucked out of the ring. Because they're getting sucked out of the ring, the delocalization starts to plummet. It's not really a good nucleophile anymore. Because the definition of a nucleophile is it's negative. And that group is pulling those negatives out of the ring, which deactivates the ring. So these are the two classifications that we need to talk about. Okay, now let's look at this in a little bit more detail. Let's start with our electron donators. These are activators. These are just examples of activators. Just examples, that's all they are. But if you look in each one of these cases, you have a group that has a set of electrons. Right there it is. This OH, there's a set of electrons. Here's an ether, ROR, there's a set of electrons. So if the atom that is directly connected to the ring has a set of electrons like this, then those electrons can be donated to the ring. They can participate in delocalization. We've increased the number of electrons that can swim around in that benzene ring. We've made benzene a better nucleophile because of it, because there's more negatives, and the benzene will become activated, and it's more willing to participate in a reaction versus the normal run-of-the-mill benzene with nothing on it. So if I add an amine, a hydroxyl group, an alcohol, or an ether group, each one of these activates the ring and it makes it more reactive. However, if I have something on the ring, like a positive NH3, that positive charge is going to suck electrons out of that ring. And if it sucks electrons out of the ring, it destroys the delocalization. It makes that benzene weaker as far as nucleophile goes. The electrons are spread out more over an area. This is going to be a problem. And because of that, it withdraws the electrons from the ring, making benzene a weaker nucleophile, and it makes it more stubborn in the reaction. Now, these are not the only things that we can talk about, right? I mean, this is a deactivator. This is a protonated amine that's a deactivator here. In the other slide, you saw amines and OHs and ORs as activators. But folks, that's only the skim of the top of the benzene reactions and the benzene substituents. Here's more of a chart that shows a number of different functional groups that we have worked with up to this point. And this chart's pretty important. I'm not going to tell you to memorize the chart. I actually do not want you to memorize the chart at all. You're going to be able to use this chart when you have to. But I want you to understand what the chart is trying to tell you. So in the middle of this chart, you're going to see a hydrogen that's right here. This hydrogen's kind of benzene, just normal run-of-the-mill benzene. There's no groups on it at all, and benzene has a certain reactivity, and we know that what that reaction rate is going to be. And then we compare everything else to that benzene. So everything is getting compared to a hydrogen. That's how this chart is broken apart. So above the hydrogen, what are you going to see? Look at this. Above the hydrogen, weakly activating, moderately activating, strongly activating. All of those are your activator groups. Down below hydrogen, weakly deactivating, moderately deactivating, strongly deactivating. That means that benzene is a poor nucleophile. It can still react. Don't take me the wrong way. It can still undergo a reaction. But as far as definition of a nucleophile goes, it's a little different. The group is affecting it in a different way. In addition to this chart is going to tell you another tidbit of information. Really the piece that's most important to us. And in that other column, you're going to see what we call a director. Okay. A director basically means that your strongly activating group and your moderately activating group and your weakly activating group and even your weak deactivators, all of that grouping right in there, will direct that incoming piece to a ortho or para position. OP. What? Okay. He's losing me now. What does he mean by that? Okay, well, here's the thing. If I have a benzene ring, there we go. If I have that benzene ring and it has something on it like an OH group, and this OH group is seeing another group coming in to react, that OH group is going to start directing traffic. Imagine being on a runway with airplanes coming in. OH is on that runway with the bright orange cones. And it's seeing this airplane come in, another nucleophile. It doesn't matter what that other nucleophile is. Who cares? It doesn't matter. But an incoming, or an electrophile, sorry. But an incoming electrophile will come in and OH goes, oh no, get my orange cones. I'm going to have to direct the traffic here so that way it doesn't get kind of bogged down. OH, by definition, is an activator. We see that right up here. OH, also, by the way, is a ortho-para director. So what that means is that when this electrophile, whatever electrophile comes in, the OH group will say, stop, wait a minute. I'm the OH here. I was here first. I'm going to tell you where to go. And OH says, I'm giving you 2 spots that you can park your tush in. Your first spot is the ortho to me, and the second spot is the paro to me. You make up your mind on which one you want. That is the ortho-para director. OH does it, NH2 does it, NHC double bond OR does it, the R group, which is a normal carbon chain, does it, the AR group, aryl, that means another benzene ring will do it, a CH double bond CH, an alkene part will do it, your fluoros, your chloros, your bromos, your iodos will do it. They all direct it to the same spot, and that spot is O and P. Now down below, take a look at what's down below. These moderate deactivators and strongly deactivators, folks, all of these are your meta directors that you're seeing at the bottom. Again, what does that mean to me? Well, that means that with a benzene ring, If the benzene ring has one of those groups on it, like a C double bond OH, that's a benzaldehyde. If another electrophile comes into the picture, meow, and for the landing, that benzaldehyde group, the aldehyde group, says, wait a minute, orange cones, orange cones, orange cones, I'm out. I'm going to be directing the traffic. I was here first. I'm going to tell you where you need to go, and you can't boss me around. And that C double bond OH basically tells that incoming group, listen, you have one spot only to go to, and that one spot is going to be a meta position to me. OMP, Becky, look at that ring. There's a group on that ring telling another group where to go. Can you believe the gall that that group has? That's the way that this world works. So the aldehyde group is a meta director. It sees this incoming group that will be attaching itself to the ring. It can't really stop it. The only thing that it can do is tell it where to go. And maybe flips it off too at the same time. Well, if you need a closer look at this chart, here's the same chart that's zoomed in just a little bit. All of these are your activators, and they are grouped into weak, moderate, and strong. And all of these are also ortho-para directors. You'll also find this chart in your text, and you'll also find this chart available to you in the lecture module folder, because this is a pretty important chart that you've got to use and that you have to understand. All right? Okay. Deactivators, same deal here. All of these are deactivators. The majority of them are meta directors, except for the first grouping at the top of your halogens. And those halogens are not meta. These halogens are O's and P's. It's kind of weird how they're breaking up and why they're breaking up that way, but that's the way that it works. So the moderate and the strong are going to be meta directors. All right, folks. So I think that's enough to turn on. Okay, and the reason that I say that is because we're going to have to basically use this now to our advantage. We're going to have to be able to use the chart. We're going to have to describe why reactions are happening the way that the reactions are working. But again, as a review, please understand that the group is an activator because it has electrons that it's donating to the ring and participating in the delocalization. So these are moderately activators, and you can see that the atom that's directly attached to the benzene ring has a pair of electrons that it can use and donate for that purpose, which is very good, right? But if you take a look at the deactivators are suckers. They are electron suckers. In each one of these cases, look at that carbon to the left. That carbon is getting used and abused by that oxygen that's on it in the double bond. That oxygen wants and wants and wants and wants and wants, and carbon can't really do anything about it. It just says, okay, here's the checkbook. And that oxygen goes and takes off and never comes back. Well, that carbon is getting sucked of electrons by that oxygen, and it's becoming short. It's going to call its buddy. It's going to go, hey, you got to bail me out. I mean, my bank account's getting ready to go negative. This oxygen, all it wants to do is to go out and eat fancy dinners and watch movies all the time, and I've got to take it on these real big expensive trips, and it never leaves me alone. It just wants everything that I've got. So you're going to have to bail me out a little bit so that way I can put my money in my bank account. And that carbon in the benzene ring says, okay, I got you back, but this is not a long-term solution, but I've got your back. So that carbon is an electron sucker. It pulls electrons away from the benzene because of the electronegativity difference between the carbon and the oxygen. Oxygen has a higher electronegativity value, which means that it pulls the electrons away from carbon, which means that that makes that carbon a partial positive charge, and that partial positive charge is attracted by the electrons in the benzene ring. The aldehyde group does it, which is what you see on the left. The ketone group does it, which is what you'll see second. The ester group does it, which is what you see third. And the carboxylic acid group does it as well, which is what you see fourth. All of those are electron pullers away from the ring, which makes them a deactivator. Down at the bottom of that chart, you see strong deactivators. And folks, it's the same concept. It's the same reason. That nitrogen is getting pulled by two electronegative oxygens. That makes this a positive, full-blown positive charge. And therefore, those electrons in that ring can go right over to that nitrogen. The same thing's happening here with the nitrile group. Nitrogen wants and wants and wants and wants and wants. That carbon is a partial positive, and it pulls the electrons away from the benzene. The S group, the N group here, all does the same thing. Look at all of those electronegative oxygens around the SO3H group. That's that sulfonate group that we use sulfuric acid with, right? The NO2 group that I see in the beginning, that NO2 group probably came from a nitration of a benzene. I added nitric acid and sulfuric acid to get my NO2 group on. That's what that group is, NO2. We've just not drawn it that way, but that's how we've been writing it. So this is the breakdown of an activator and a deactivator. So here's an example problem I want you to work on before you hit play on the next video. List the compounds in each set in order of decreasing reactivity toward electrophilic aromatic substitution. So that means in order of decreasing reactivity. They want me to have the really active ones in the beginning, and they want me to end up with the ones that are not very reactive last. Use the activator chart. Go back. Use this master chart of activators and deactivators in order to answer that question. To do that, though, you'll have to understand the terminology and IUPAC of benzene. Oh, look at there. Look how they wrap those two concepts together, because look at A, benzene, phenol, toluene, nitrobenzene, bromobenzene. Can you draw the structures of each one of those? I hope so, because we just did it in the first half of this lecture module. And if I look at B, dichloromethylbenzene, difluoromethylbenzene, toluene, chloromethylbenzene. Can you draw those structures? Because only when you draw those structures can you compare those structures to that chart. So here's a combination of a nomenclature question as well as a reaction question. Which one is going to be the best reactor? Which one will be the poorest reactor? And rank all of the others in between. So use the reaction chart, the activator-deactivator chart, and I think that you'll be able to answer this question without a problem. So try it. Again, you never know. You might get it right. You might get it wrong. And then hit play on the next video to understand why you got it right. Maybe it was a lucky guess. Or why you got it wrong. I love when people get questions wrong, though. It makes me happy for the day.